Hi all. Today we can discuss our fourth module, reluctance motors. In this module, we have to discuss reluctance motor and its working principles, advantage, disadvantage, construction. Also, switched reluctance motor, its analysis, its operation, advantage, disadvantage, etc. Okay, we can start with the reluctance motor. Before going to reluctance motors, we need to know what is reluctance. What is reluctance? It is the opposition offered to magnetic field lines. That is similar to that of resistance in electric circuit. Reluctance is in the magnetic circuit. Therefore, a motor that is worked based on the principle of minimum reluctance is called reluctance motor. And we are already familiar with the variable reluctance stepper motor. How a variable reluctance stepper motor works? While we are energizing our stator circuit, the rotor will rotate in the principle of occurring in a minimum reluctance position. Like that, a reluctance motor is similar to that of a variable reluctance stepper motor, but the difference is that the stepper motor rotates in step by step manner based on our step impulses, but reluctance motor is a continuously rotating motor based on principle of minimum reluctance. The most commonly used types of single phase synchronous motors are reluctance motor and hysteresis motor. We have already studied hysteresis motor in module 3. That is, a reluctance motor is a single phase synchronous motor, that is rotating synchronous speed. The motors operates from single phase AC supply, and similar to that of it has a similarity to the single phase induction motor, and its output is mainly for low power applications, and the overall performance is quite good, and motors having constant speed characteristics. That is, the main advantage of a synchronous motor is that you're having a constant speed characteristics. Now we can go for construction of a reluctance motor. Already we have discussed that it's a single phase similar to that of a single phase induction motor. That is, it has a stator, a rotor. In stator there is mainly two windings. This is the main winding and this is the starting winding. For what we are using a starting winding? We are already discussed in single phase induction motor. For starting a single phase motor we need a starting winding. Okay, now an induction motor with a modified squirrel cage motor. Reluctance motor is actually a split phase induction motor with salient poles. That is, in a squirrel cage induction motor the rotor is similar to that of a squirrel cage, but in a reluctance motor it has a salient pole rotor we are using. Stator, similar to that of any one of the single phase induction motor, the stator has two windings, the main winding and an auxiliary winding. In single phase induction motor, our starting winding is cut using starting circuit is eliminated using a centrifugal switch, while it gained the 75% of the synchronous speed. Similar to that of we are use arrangement is using in this motor also. Therefore we can cut the starting winding when the motor gains sufficient speed. The starting switch is connected in series with the auxiliary winding. Rotor, made up of ferromagnetic material and is almost similar to that of a squirrel cage motor, except some rotor teeth are removed at an appropriate place to produce salient poles. Okay, in this figure we can see that this is a reluctance motor. that is a salient pole. For variable reluctance we need to have salient poles, and here this is the pole and this is the notch area, and we are inserting this rotor in a circular stator periphery. We can see that in this area air gap is minimum compared to this notch area. Okay, therefore in pole area reluctance is minimum, and in notch area reluctance is maximum. If we remove teeth from four location, then we can produce a four pole salient pole structure that is shown in this figure. Here we are removing, okay, removing portions from this area. Each slot of rotor is provided with a rotor bar made up of aluminum or copper, which are short circuited by a pair of end rings, as in case of a squirrel cage induction motor. Okay, in squirrel cage induction motor, we are using end rings. For what? For the working of induction motor, it need a closed circuit. Then only, due to induced EMF and a current will flow through the rotor. For that arrangement, we are using an end ring. Here also for starting, we need this induction phenomena. Therefore, we are also using end rings. Now, different types of rotor construction. First one, notch type rotor. Here notch areas are high reluctance. This is the pole area, this is the notch area. Pole areas are known as salient poles, that is minimal reluctance. Notch area, there is more air gap, therefore high reluctance. Flat and barrier slot rotors, and this is the another type of rotor, flat. Here we can see that this is the pole area, this is the flat area, and comparing to this pole, the flat area, if we are using a round stator, in flat area there is air gap is high compared to that of pole area, therefore variable reluctance can be achieved through this arrangement. This is the flat slot rotors. Next, barrier slot rotors. Here we can see that in order to increase the air gap, they are insert a barrier slot in the rotor. Therefore, there are four. We can see there are four barrier slots in this rotor. Therefore, in this position, the reluctance is high compared to that of pole position. Here, there is air gap is low, and this also helps to achieve the variable reluctance condition. Now the operation, we can discuss how it will operate. Okay, when the stator of the reluctance motor is supplied with a single phase AC supply, the motor start as an induction motor. We are discussed in already discussed in single phase induction motors working principles. The starting or centrifugal switch disconnects auxiliary winding of the motor at speed of 75% of the synchronous speed. I already discussed what is happening, and rotor accelerate towards synchronous speed. Now in this is a very important figure. We can see that these are the magnetic field lines coming from the stator and going through the rotor to the stator again. Okay, now this is the rotor is in line with this magnetic field lines. That is, this is the position where reluctance is very low, that is minimum reluctance position. The magnetic flux line can easily flow through this rotor circuit. And in this figure, okay, in this figure the rotor is not in line with the magnetic field lines. That is, reluctance is increased. Okay, comparing to the first figure, in this figure magnetic field lines have some had to, it's not straight line. Okay, here again, uh, magnetic field lines increased, overstretched. The flux path is overstretched here. Okay, therefore in the first figure, here there is no stretching in the magnetic field lines, therefore this is the minimum reluctance position. Okay, when the reluctance motor starts to run at a speed close to synchronous speed, a reluctance torque is produced. How a reluctance torque is produced? Since the rotor will align in this minimum reluctance position, therefore the rotor try to continue in this minimum reluctance position and try to rotate in synchronous speed, so that similar, so that the with the rotating magnetic field the rotor also try to rotate. That is called reluctance torque. At a critical speed, the low reluctance path provided by the salient poles will cause them to snap into synchronism with the rotating flux. That is, the rotor aligns itself in minimum reluctance position. For aligning the minimum reluctance position, a rotor rotates in synchronizing with our rotating flux. Okay, due to this phenomena, it experiences a torque called reluctance torque. When the rotor synchronizes, slip is equal to 0. What is slip? Difference between synchronous speed and a rotor rotating speed. Okay, therefore the rotor synchronizes, the slip is equal to 0. Now the rotor pulled around by reluctance torque. Figure at the right show the rotor synchronized at no load, and here at no load the rotor is synchronized, that is the rotor is aligned in low reluctance position, that is the magnetic field lines can easily flow through this rotor. Okay, that is the minimum reluctance position. Now we have the equation for reluctance torque. T reluctance is equal to K into V by F the whole square into sine into 2 delta reluctance. Here T reluctance means average value of reluctance torque. V is the applied voltage V. F is the line frequency in hertz. Delta reluctance is the torque angle, and we can explain what is torque angle and what are the significance of torque angle in the following slides. K is the motor constant, and maximum reluctance torque T reluctance max occurs at a delta reluctance is equal to 45 degree. Okay, now in the first figure, in this figure, this is the minimum reluctance position of the lot of the rotor at no load condition. Okay, at this condition, if we are giving a load to the rotor, what happened? The rotor poles lag the stator poles, that is there should be a lagging between rotor poles and stator poles, and the angle of lag delta is called torque angle, and we can see that torque angle, this is the torque angle, and if you are giving a load, what happened? The rotor lags an angle, that lagging angle is called torque angle. The motor adjusts its torque angle for change in load as in three-phase synchronous motor. We are already studied in S4 sim. For that we have discussed what is torque angle. So for a motor, a synchronous motor, if you're varying the load, what happened? For adjusting the torque, angle with change in load. Now in this figure we can see that operation at a maximum load, that is our load is increased to maximum. Here torque angle is delta is equal to 45 degree. Okay, that is stretch, our flux path is overstretched and rotor falls out of synchronism. And if we are increasing the load beyond this point, what happened? Our rotor cannot follow the stator flux. Okay, that is out of synchronism. The motor runs at a slip speed. Therefore operation at a maximum load at means at when load angle is at a 45 degree. Reluctance motors are subjected to cogging at the time of starting, and cogging we are studied in synchronous induction motor. Cogging is the locking tendency of a rotor which can be minimized by skewing the rotor bars and not making the number of rotor slots equal to an exact multiple of the number of poles. And the reluctance motors also subjected to cogging at the time of starting. Okay, now speed torque characteristics of reluctance motor. Okay, from this scala we can see that here is the torque, here is the speed. Therefore initially we are using main winding and auxiliary winding. Since we are using auxiliary winding, our starting torque is very high. Okay, if we are using only main winding, our starting torque is zero, but we are using an auxiliary winding, our starting torque is increased. Okay, and it's almost a constant torque. Okay, almost working based on almost in constant torque. The starting torque depends upon the rotor position. The value of the starting torque varies between 300 to 400 percentage of its full load torque. Okay, and all these points we already discussed. We just go through these points. Now, what are the types of reluctance motors? First one, variable reluctance stepper motor, switched reluctance motor, synchronous reluctance motor. Variable reluctance stepper motor we are already discussed. Switched reluctance motor we will discuss in the following the next slides. Synchronous reluctance motor also we will discuss. Okay, now actually reluctance motor is the major classification, and under that reluctance motor there are several motors working based on the principles of reluctance. Okay, now advantages: the reluctance motors have simple construction, they don't have brushes, commutators, permanent magnets, hence they need less maintenance and are spark free. In DC motors we are using brushes, commutators, etc. In this reluctance motor, no need of any commutators or brushes. We are giving a supply, a single phase supply in the stator, and rotor is salient pole, therefore no need of brushes or commutators. Reluctance motors do not need any mode of DC excitation. Okay, no need of any DC excitation is required. It has in synchronous motor what we had to provide a DC excitation in the rotor, and in the reluctance motor no need of any DC excitation. It has very high starting torque. So its starting torque is very high. It can provide a very accurate speed control even in open loop control. That is the main advantage of a reluctance motor. Now disadvantages: it is less cost effective, it has low efficiency. The reluctance motors work on low power factor, similar to that of induction motors worked on low power factor. Size of such motors are larger than equivalent synchronous motor. Comparing to size of a synchronous motor, size of reluctance motor is large. And these are the main disadvantages of a general reluctance motor. Now, what are the applications? For timing devices, recording instruments in textile machineries, signaling devices, control apparatus, automatic regulators, teleprinters, gramophone. These are the major applications of reluctance motor. Okay, so we can wind up this section. Now we can discuss the switched reluctance motor in detail in the next section. Thank you.